Welcome. This is going to be quite a long one since I'm going to be covering all of the radioactivity section one way or another over the next 15 to 20 minutes. It might take longer. If you're watching this on YouTube, you'll find in the description time references so you can find the section you want easily. Let's get started. I'm going to do this in order and I'm going to start with atomic structure. Hopefully you're familiar with the basic structure of an atom consisting of a nucleus and then the electrons orbiting in shells. Okay, so inside the nucleus we've got protons and neutrons, which collectively you can describe as nucleons, particles which form the nucleus. A little bit on notation. So let's take a general element and I'm going to call it X. That will have a certain number of protons in the nucleus, a certain number of neutrons in the nucleus, and a certain number of electrons orbiting. Let's talk about neutral atoms. You can write symbolically elements like this with an atomic number or proton number and a mass number or nucleon number. A couple of examples. Carbon, 6 protons in the nucleus, so the atomic number is 6. There are 6 neutrons joining the protons in the nucleus, so the total mass number is 12. The number of neutrons can be calculated by taking the mass number and subtracting the number of protons. That gives the number of neutrons. The number of electrons for a neutral atom is the same as the number of protons. Another example would be uranium, 23892. So in this case, there'll be 92 protons, 238 minus 92 neutrons, so that would be 146, and then 92 electrons, since the number of electrons is the same as the number of protons. Okay, so you should also be aware that an isotope, in fact, you can write the definition of an isotope yourself. Pause the video and have a go. Now, answer in 3, 2, 1. The most important words here are same and different. So it's same number of protons and a different number of neutrons. What makes a particular element that element is the number of protons in the nucleus. If the number of protons were to change, you'd have a different element. So it's only the number of neutrons which is affected, which affects things like the mass of the atom, the physical properties, rather than the chemical properties. Examples of isotopes. Well, hydrogen exists in 3 forms, hydrogen 1, 2 and 3. These have different abundances. Hydrogen's definitely the most abundant in the universe. Deuterium or hydrogen-2, less so, and tritium is only found in trace amounts. 2 other examples I've got here. I've got carbon and its 4 main isotopes, and beryllium and its 3 main isotopes. You can see here, what's quite nice here is it tells you the abundances. Syn, by the way, means it's synthetic. It can only be man-made. You'll notice that there's a difference in what's called the half-life, and we're going to come to this later on. It varies between here 20 minutes for carbon-11 and to 1.39 times 10 to the 6 years, or 1.4 million years for beryllium-10. It also tells you what the most common, or what the decay mode, or what type of radiation each of these decays by. At IGCSE, we only need to know alpha, beta, gamma, and then something called neutron emission. Okay, so don't worry too much about these beta pluses and this electron, this epsilon, I should say, at the top here. That brings me on quite nicely to radiation. Now, what I'd like you to do is pause the video and have a go at filling in this table for alpha, beta, and gamma radiation. So pause the video and have a go at that now. Answers in 3, 2, 1. So there are the answers. Let me apologise for the creaking that you can hear. I've swapped chair, so hopefully we'll avoid any more of that. So notice I inserted the words relative because when we talk about charge and mass, when we talk about small particles like radioactive particles and protons and neutrons, we use relative units. So we make a proton have a relative mass of 1 and a relative charge of +1, and then compare everything to the proton. You'll notice that penetrating power increases from alpha to gamma, and you'll hopefully remember that from alpha to gamma, ionizing strength decreases. So alpha is the most ionizing and gamma is the least ionizing. These two properties are related. If this is a block of matter and I've got a particle, let's say I've got an alpha particle with a relative charge of +2, and remember an alpha particle, relative mass of 4 is much more massive than an electron or a beta particle. You can imagine if we've got atoms inside this material, let's say we've got a solid, so we've got the atoms arranged like this. As the alpha particle passes through, it's got a doubly positive charge and it's a large object in comparison to either a beta or gamma. So it's much more likely to knock an electron out of an atom it's passing and transfer some of its energy. A beta particle is much smaller, only -1 charge, relative charge, so it's much less likely to knock an electron out or cause ionization in the material. A gamma ray electromagnetic wave has no charge or mass. Therefore, while it will cause ionization weakly, but it will tend to pass through without causing much ionization, and hence it won't lose much energy. So the more ionization a particle causes, so the more it tends to knock electrons out or ionize atoms in a material, the more energy it will lose. And if you lose more energy, you're not going to penetrate as far. Okay, so that's why decreasing ionizing strength tallies with increasing penetrating power. Before I start talking about the different types of decay and decay equations, what I'd like to do is just talk about decay generally. Certain isotopes, so let's say this is an isotope, are unstable. And at some point, they'll emit a particle and change to become another nucleus, or change in some respect. So the types of decay we need to know about alpha, beta, gamma, and neutron emission. Properties of radioactive decay are that it is a random process, so you can't predict when a particular atom or nucleus will decay. You can only give some probability of it decaying within a certain period of time. And the other property is that it's spontaneous, which means that it just happens. It doesn't need an external stimulus to initiate it or cause it. And it also means no external factor will affect the rate of decay. So you can't change the rate of decay or the half-life of a substance by heating it or subjecting it to a magnetic field or anything like that. So the characteristics then of radioactive decay are that it's random and spontaneous. Now let's look at some decay equations. So I've prepared over here some of these equations that we're going to fill in. You'll notice that these equations are of a similar form. So we start with a parent nucleus. We end up with a daughter nucleus. The nucleus will change in some respect and will emit a type of radiation. Starting with alpha then. An alpha particle is written alpha and it has a proton number of 2, an atomic number of 2 and a mass number of 4. Now the rule is that the total atomic number has to balance, so the total atomic number on the right hand side has to add to whatever it was on the left hand side, and similarly for the mass numbers up here, they have to all balance. So in this case, if an alpha particle is emitted, the proton number of the daughter nucleus must be 2 lower than it was before. Similarly, the mass number must be 4 less than it was before. An example of alpha decay, I'm going to write in green below now. You'll notice that if you look at the mass number, it's gone from 238 to 234, down by 4. And the atomic number's gone down by 2 from 92 to 90 because there are 2 protons in an alpha particle. Beta decay involves the emission of an electron, which we write as a beta. It has negligible mass, so we write a mass number of 0. It's convention to write the charge of the electron down in the atomic number space. That means that our balancing rule will work. And that means that the proton number here must go up by 1, so that z plus 1 plus minus 1 gives back z. The mass number is unaffected. So an example of beta decay is the decay of carbon-14 into nitrogen-14. You'll notice the proton number has increased by 1, and the balancing rule works out both for mass number and atomic number. Gamma emission or decay involves the emission of a gamma ray, 0 mass, 0 charge. So in fact, the nucleus is unaffected What's the point of that, you might think? Well, sometimes after an alpha or beta decay, particularly, a nucleus can be left in what's called an excited state, which means it has more energy than it needs. And one way to get rid of this energy is by emitting a gamma ray. So gamma emission often follows alpha or beta decay. And in fact, if you have an alpha emitter, say you had some americium that was an alpha emitter, you'd also find it would be emitting gamma rays, because some of the decay products of the americium, the daughter nuclei that result from the decay of americium, would have a bit more energy than they need and then release a gamma ray to get rid of that excess energy. So that's gamma emission. An example would be the gamma emission from cobalt-60, which I've drawn there. Move on to our last type of decay, which is neutron emission. This involves the emission of a neutron, mass number 1, atomic number 0. That means the proton number will stay the same and the mass number has to go down by 1 so that the mass numbers balance either side. An example of this would be the decay of beryllium-13 into beryllium-12, the equation for which you can now see. Let me give you the opportunity to do some examples. So, have a go at those. You can pause the video, possibly sketch them down on some paper, or at least think what the answer should be. Answers in 3, 2, 1. Note, you will always be given enough information to work out what type of radiation is emitted, the mass or atomic numbers of the daughter or parent nucleus, and if an element name is required or element symbol is required, you'll be given enough information like part of a periodic table to help you do that. What I'd like to do next is discuss decay a little bit more. Here's a video I prepared earlier. I'm going to play it. What it shows is an animation of 4,000 protactinium-234 atoms undergoing a simulated decay. Note, the process is random. You can't predict which nucleus will decay when. Also notice that as we end up with fewer protactinium atoms or nuclei, the number that are decaying per second gets lower. Let's play this now. So the red circles represent the protactinium which hasn't decayed. So the blue circles represent the daughter nuclei which are produced. So you can see that you can't predict when a particular nucleus will decay. So it's just a simulation of the decay process. Next, what I'd like to do is just move over here for a minute. So this is another animation. And what it shows is a Geiger-Müller tube connected to a counter, which I've got close to a source. Now, this animation shows the radioactive particles being emitted. So I'm going to go ahead and play it and then talk over it. So you can hear the clicks, the count rate is here, and you can see the count rate changes as I bring the Geiger-Müller tube closer and further away from the source. Okay. What I'm going to do now is take the source away. You can still see there's radiation flying around, there's background radiation, so we're still getting a small count rate, but it's very much reduced. We're only getting a background count rate at that point. I'd like to make an important point here. If I play this again without the sound, you will notice that this source is emitting a large number of particles per second. In comparison to the number that are being detected by this counter, that we're only detecting the particles which are emitted along a very narrow range of directions. There's a big difference between the activity, right, which is the number of decays that the source is experiencing per second in total, and what you'd call the count rate, which only tells us the decays which are being detected by the counter because of the radiation incident on it. So the count rate is a certain fraction of the activity. Clearly, if the activity decreases, then you'd expect the count rate to by the same factor. It brings me on to another interesting point, which is, in fact, as well as detecting the radiation from this source, we're also detecting the background radiation. So our count rate is going to be slightly too high. So what you need to do experimentally is to measure the background count rate beforehand for 5 or 10 minutes, work out the background count rate per second, and then subtract that from the count rate you get with the source present to get what you'd call the corrected count rate. Imagine I wanted to investigate the decay of a source using a detector which was connected, a Geiger-Müller tube connected to a counter. Let me construct a table. What I would do first is measure the background count rate without the source present. So let's get rid of the source and let's measure the background count rate. So 2 counts per second is quite large. However, let's go with it in this case. To measure the background count rate, you'd simply leave the Geiger-Müller tube connected to the counter, switched on for perhaps 10 minutes, so 600 seconds. Measure the total count rate and then divide it by the number of seconds, in that case 600, to get the number of counts due to background radiation per second. You then reintroduce the source. Now let's say this is a pure substance, so one particular radioisotope, and then you'd have the detector a certain distance away, keep that the same throughout, and perhaps every 10 seconds you would then take a reading of the count rate. Say we do this and we get the data as follows. So you can see the count rate is decreasing over time as the amount of radioactive material we've got is reducing. What I'd need to do to get the corrected count rate, which is the count rate due to only our source and not the background, is subtract our background count rate of 2 off all of these. If we were to then plot the corrected count rate against the time elapsed, we would get this graph. So this shows the decay of the count rate as time progresses. You can see it's got that classic exponential decay shape. Although we've plotted the corrected count rate, which amounts to the number of decays we're actually measuring with the detector, the actual activity of the source, the total number of decays it was experiencing, and also the number of nuclei present would actually behave in a very similar way. You get this decay. I'd like you now to have a go at writing 2 definitions for half-life before I carry on. So pause the video now and write 2 definitions for half-life. Answers in 3, 2, 1. Okay, so here are the 2 definitions. The time taken for the number of parent atoms or nuclei in a radioactive sample to halve, or the time taken for the activity of the original substance to fall to half its initial level. So both the activity and the number of parent atoms remaining are proportional to one another. So this is a sort of idealized graph where we start with, you see, 400 counts per second. And the half-life here is the time taken to fall to half that, which is 200. So if we were to read off the half-life on this graph, we'd expect it to be looks about 15 hours. If we then looked at the next half-life, 200 to 100, we'd expect then that to occur 2 half-lives later, 30, which is 2 lots of 15 hours. Okay, so we could even go to 50. We'd expect it to have halved again after 45, which is 3 lots of the half-life, 3 lots of 15 hours. You'll see I've reproduced this below. Okay, so this graph is dealing with counts per second, which is the number, remember, the number of decays that are actually detected. The activity, the total number of decays per second, would also behave in this way. Obviously, the numbers would be higher. Activity, when you're actually measuring activity, specifically the total number of decays, you use the unit becquerel, spelt Becquerel, and that tells you the total number of decays per second. Okay, so it's not quite the same as counts per second, because counts per second only is what you detect, but the total number of decays in the source per second is what's considered the activity in becquerels. Now I'd like you to have a go at these 2 examples using half-life. So pause the video and have a go at those 2 calculations. Now remember, IGCSE problems only work in whole half-lives or multiples of the half-life. Answers in 3, 2, 1. Okay, there are the answers. You can compare them with what I've done. Notice the second one is made easier because I told you that IGCSE questions only work in whole half-lives. So if you work out how many times you have to halve 120 to get to 1.88, see how many half-lives that is, how many times you have to half it, then do the sum that I've done in the second half of that slide to get 1.17 minutes or 70 seconds. Next, uses of radioactivity. When you're looking at uses of radioactivity, you want to consider two things. You want to consider the half-life of the radioactive source you're going to use for a particular application, and you want to consider the type of radiation that's emitted. For each of these uses that I've got in these diagrams, what I'd like you to do is pause the video, identify the use first of all, but think about or write down on a piece of paper what half-life range you'd expect to be necessary for your source, and also what type of radiation do you think needs to be emitted. Pause the video and do that now. Answers in 3, 2, 1. So really, you want thickness monitoring, because thickness monitoring and cancer treatment equipment you want to last for a good amount of time. I would say between 50 to 100 years half-life would be suitable. You don't want your source running out and need to be replaced all the time. You want beta for this thickness monitoring because you can adjust aluminium foil is a suitable material to look at the thickness of, given the penetrating characteristics of beta. Beta is stopped by a few millimeters of aluminium. At different thicknesses, you'd get different amounts of beta getting through. So you could actually set the computer to adjust the rollers here based on a particular level of beta radiation getting through, depending on the thickness of the aluminium. For cancer treatment, again, you'd want something which could penetrate the body to reach the cancer cells inside the body. Medical tracers, you want them to be gamma so they can get out of the body and be detected. Half-life 6 to 8 hours. You don't want it lingering, the radioactive material, once the person's left the hospital. Leak detection, you'd want 1 or 2 days probably. You know, if it was a complicated water pipeline network, and you'd want it to be gamma radiation so it could be detected above ground and get through these layers of soil. For a smoke detector, you want alpha particles. They're stopped by or absorbed by smoke particles getting into this region here. So you would no longer get the alpha particles being attracted towards the negative plate being registered as a current, because the smoke particles would absorb them. A couple of other smaller points. First of all, background radiation. There are different sources you need to know about. Radon in the earth, or that comes from the ground, is a major one. Cosmic rays from the sun, from space. Food, like things like bananas, contain radioactive materials. In fact, all living material to some extent contains radioactive material. Medical appliances and applications in hospitals, X-rays account for some of the background radiation, nuclear waste, nuclear fallout, and of course air travel. You need to remember all of these so you can give them as examples in an exam. Another little snippet is the difference between contamination and irradiation. So if I were to take, I don't know, an apple, and I were to have a source out here which had a radioisotope in it and it was emitting radiation, the radiation might cause some ionization within the apple, but there would be no radioactive nuclei actually in the apple. There might be a few ions, but not radioactive nuclei. So in that sense, the apple would be irradiated. It would have had radiation incident on it, but it wouldn't have no radioactive material within it. If we were to take the apple and take the radioactive source and then actually put the source into the apple, then the apple would now contain radioactive atoms. It would be a radioactive object and would emit radiation itself. So in that situation, it would be contaminated with radioactive material. So there's a big difference between contamination and irradiation. Another thing which isn't on the syllabus, but I'd like to give you a chance to think about, is carbon dating. Carbon dating is an application of radioactivity which relies on the fact that in the atmosphere, cosmic rays turn some of the nitrogen into carbon-14, the radioactive isotope of carbon, which decays to nitrogen-14, back to nitrogen-14 via beta emission. Okay, so this carbon-14 gets into plants because plants absorb carbon dioxide during photosynthesis, And ultimately that carbon-14 finds its way into animals which eat the plants, and then our cells which eat animals and plants. So all living materials contain a certain amount of this carbon-14. Now, since the carbon-14 is being constantly replenished up here, so constantly being added to the atmosphere by cosmic ray interactions, and it's constantly decaying, so the carbon-14 which is in the plants and animals is decaying, so being taken out of the system at a certain rate that's governed by the half-life of carbon-14, which is about 5,760 years, an equilibrium's established. So whenever you have a system which has an input which is constant and an output which is constant, what will happen is you'll find a particular level, a certain percentage of the carbon in living things will be carbon-14, which means the activity you'd expect from a certain mass, say we had a gram of material, the activity you'd expect due to carbon-14 from a given mass of carbon would be constant, okay? And while the carbon's being replenished inside a living thing by either taking in carbon dioxide through to photosynthesis or carbon via eating of plant material, you'd expect the level of carbon-14 in a living object to be the same. When something dies, they stop taking in carbon. The carbon-14 stops being replenished, and therefore the activity, compared to when the object's living, will decay over time as the carbon-14 within it decays. So if you can get some idea of the activity of a particular object due to carbon-14 at any particular instant, you can estimate its age because you know how much the activity should have reduced from the level which you could theoretically calculate using, the processes which are going on up here. Okay. Now, carbon-14 is good for dating things up to sort of 50,000 years ago, 50,000 years ago, because the half-life of 5,760 years allows us to measure timescales which are perhaps up to 10 times the half-life, certainly not more. Once 10 half-lives have elapsed, there'd be not enough carbon-14 in present anymore to really get a detectable signal. So if you want to calculate or estimate the age of things over the millions, billions of years, you can't use carbon dating. You actually have to use another type of dating. There are different types using uranium, rubidium, and other elements. Okay, what I'd like you to do now is attempt, there are 2 GCSE style questions here, so have a go at this one first. So pause the video, have a go, you can sketch the answers down on a piece of paper. Now, answers in 3, 2, 1. Okay, so compare your answers to mine. Notice that I've extended the line here. It looks like the line starts at 900. I don't know why that top corner has been erased. Another exam question to have a look at. This is on the uses. So pause the video and have a go at this one now. Answers in 3, 2, 1. Okay, so have a read through of my answers. Hopefully they make sense. Now, that was quite a long video. We're coming up to 29 minutes. I'm going to stop there. If we look back at the list of things you're supposed to know, we've covered all of those. In the next Topic 7 video, we'll look at fission and fusion.